Hi there. So, in this tutorial, I'm going to be guiding you through the mnist CNN example in the keras guide from RStudio. So yeah, this guide is going to be explaining how to run um, a simple convolutional neural network on the mnist image classification dataset. And so what I'm going to be trying to do is just copying this code into my R console, trying to get it to work, and trying to explain to you what's going on at every step. So let's do that. So here I'm going to just copy this first chunk. So in the previous screencast, I already had created some R code that downloads the mnist dataset with keras dataset mnist here, so I'm not going to copy that. But I am going to, let's go down here. Here I copy this data preparation block. And so what is this going to do? This is going to define a batch size for training, I think. That's going to be for our training in the SGD, stochastic gradient descent algorithm. Number of classes. This is, this is the number of classes or outputs, because there's 10 different digits. This is the number of epochs, passes through train data that we want to do. And these are the input image dimensions, 28 by 28. I think it's already stored in the data, or they define those as constants anyways. So here we've already downloaded the dataset as mnist. Here they create x train, y train, x test, y test. So let's just try to do that. And let me execute those lines of code. Execute those lines of code. Same thing here. Same thing here. So it says redefine dimension of train test inputs. Not sure exactly why they wanted to do that, but now we have, let's take a look. Now we have x train, which is this an array of 4 dimensions, or you can think about a 4-dimensional tensor, where the last dimension here only has 1 unit, so it's kind of strange. But yeah, I mean, if we look at the mnist train x in comparison, and basically this is the same thing but without that 4th dimension. I think maybe that they assume when we're working with image data we need this kind of 3 dimensions corresponding to number of pixels high, number of pixels wide, and number of different channels here. I guess this is one explicitly specifying that there's only 1 channel. So then it says transform RGB values into 0, 1 range. So let's do that. Right, so it's always important to do that step to kind of make sure that our training data are to make sure that our training data are in the 0, 1 range so that the gradient descent algorithms work appropriately. Yeah, it's called scaling the data, right? So, and yeah, so I mean, I have to make a comment about this code. It's kind of bad practice to define a variable x test and redefine it here as something else, and then redefine it again as something else in terms of itself, right? So the reason why this is bad is because here if we take the range of x test values, and here if we just execute this block of code again, you see that the range of these values have decreased now. So I'm just going to briefly refactor this code just so we can get a you know, more easily reason about that. I mean, the reason why this is bad practice is because, I mean, depending on where you're looking at in the code, you might have a different idea of what X-test should look like. So instead of doing this, why don't we just say, why don't we just define these guys like this? Right, so my R session is getting a little slow, and I think it's because these things are rather large memory, taking a lot of memory. So what I'm going to do is I'm going to just kill my R session, restart it. I'm going to do this whole training on a smaller subset. So let's do that instead. Here, I'm going to restart this, download the keras dataset again. And here I'm going to again use that stuff. And here let's do that refactor. So here, instead of defining all that there, I'm going to say mnist train x how about 1 to 1000. Let's do that. And then let's say is n row x train. How about let's define a variable n train equals 1000. 1 to n train. Here, let's give that n train as the argument there. And let's reformat that. So it's in 2 lines, easier to look at. Then the X test. So here, let's take a look at what this mnist object looks like. 60,000 and 10,000. So quite a lot of things. So why don't we just say there's 1,000 training and 1,000 test, just to simplify these things. So how about that? X. So here I changed n train to just n, so that will be maybe a lot faster for demonstration purposes. Mnist test x 1 to n comma, right? Because it's a 2D, no, a 3D array, right? 1 to n comma. And here this is going to be n. So let's see, I'm going to get rid of that definition of x train and x test. And let's execute that code and see what happens. That didn't work. I'm missing that comma after my array subset here. But so here now we have our x train, which is defined like this. And so here, in the RStudio code, they do this x train gets x train over 255. And so instead of doing that, which can be potentially very confusing, let's just put that over 255 right here in the definition of x train next test. Yeah. And even better than that, you can think about saying, max intensity. Try to isolate all of the constants if you can. That's better programming practice. You want to kind of, if you're ever repeating yourself like that, make sure you try to reduce that repetition by reduces the amount of repetition in your code by defining these kind of other variables. So max intensity not found. That's the typo. Alright, there we go. So now let's take a look at xtrain. And actually, yeah, so there's a bunch of numbers between 0 and 1. Okay, so let's go back to the tutorial. And let's see what the next step is. So after that, okay, we have train test shape. Great. I don't think I need to do that. That's just printing the dimensions of these guys. Convert class vectors to binary class matrices. Okay, let's do that. And so, yeah, again, they're doing this redefining variables thing. So why don't we just do that in the beginning and not do that redefinition? So to categorical. How about that? Right, so then we don't have any redefinition of y train and y test. So now y train is this matrix with 60,000 rows and and 10 columns. But again, let's use this n to subset those guys. 1 to n, 1 to n. So then hopefully those dimensions match up. So yeah, now there's 1,000 examples in the train and lowercase, yeah, in the train inputs and outputs. Okay, let's go back to the code. Defining the model. Let's see if that works. Oh, now I have inadvertently follow a link. So why don't we go back? Ugh, went back too far. Here we go. Okay, define the model. So let's see what that model looks like. Define and compile the model. Let's look at that code. Now our model looks like this, where we have actually quite a few layers. So this is definitely a deep neural network because there's more than one hidden layer, right? So here in the first layer, it's a two-dimensional convolution layer. Here's a second layer of two-dimensional convolution, where you see the output shapes, a different number of channels, different heights and weight values here. You have a max pooling layer, a dropout layer, which is a regularization technique that didn't really discuss yet, but you can see in the book if you're interested. You have a flattening layer, which is just reshaping these into a flat vector so that it can be used in a dense layer, a fully connected layer. And after that, another dropout layer, it's for regularization, and finally a final dense layer, which is connecting to all of the outputs. The total number of parameters here is over 1 million. So I don't know how long this is going to take to train on my 10-year-old computer, but let's take a look at that. Train model. Train on 800 samples, validate on 200 samples. So here it's giving me some status updates for every epoch. How long is it taking? And so again, yeah, I mean, it should be linear in the number of samples and the number of parameters. So here it's training for 12 epochs. It has to go through every one of the samples in the train set exactly one time in every epoch. And it updates every one of those 1 million model parameters in every epoch. So by reducing the data set size from tens of thousands to 1,000, I've effectively reduced the computation time by a factor of 10, right? So here the computation is taking 10 seconds about per epoch. So if I actually used all of those, if I use 10,000 training examples instead, I should expect that it would take about 100 seconds per epoch on this machine. So is there any other code that we can copy while we're waiting for that computation? Scores, test loss, test accuracy, let's see. So here we're still only on epoch number 10, but it should be finished in about a minute. Oh, about 10 or 15 seconds now. And after that, we should be able to evaluate our model and test that and see what it looks like. So in the tutorial, it says that, it gets some pretty good accuracy, and I suspect that we're not going to get as good accuracy as in the tutorial because we didn't use as much training data. But let's see what it looks like. Scores, model, evaluate. So it says test loss equals 0.3, test accuracy is 0.9, so about 90% accuracy. And up here it says it gets to 99.25% test accuracy. So not quite, right? So I guess that difference between 90% and 99% can be explained by the fact that I'm only using 1,000 examples instead of the full training set. So that kind of concludes my first demonstration about how to train a convolutional neural network. To review, what we did is we just basically copied the code from the RStudio tutorial. Here we have, we're using again this keras model sequential function to initialize a sequence of layers. And here the first two layers in the neural network are these two-dimensional convolutional layers. Here there's some arguments that we didn't discuss that you can play with that determine the number of filters and the size of the kernels. And there's a layer with max pooling, which is a technique that is used to induce invariance in the learned representation. And then after that, there's a couple of dropout layers for regularization, and there's some this flattened layer which allows you to use the output of the convolutional layers in these dense layers later. And then overall we have a bunch of layers. This is a deep neural network that we then use the compile function to declare what loss that we want to use. It's important to use the categorical cross entropy loss here. This is for whenever there is multi-class classification problems. And here we declare an optimization algorithm and an evaluation metric, and we use the fit function on the training data with a given batch size and a given number of epochs to train the model. The critical pre-processing steps were that we have to make sure that the arrays are the right size. So I guess when we're doing this two-dimensional convolution, in the R interface, it expects that the training data should be an array with 4 dimensions. Here we add this last dimension with a size of just 1. So the last dimension corresponds to the channel. You might want to use it with more than one here if you have different channels, like say a multi-channel image, like RGB channels. Like here we're just talking about grayscale images, so we only have gray pixel intensity, so we leave it at 1. But the important thing is that here the train and X test data have to be in this 4-dimensional tensor shape before we pass it as training data to this kind of a convolutional network with 2-dimensional convolution. Okay, so thanks for listening, and hope you learned something about convolutional neural networks.